Okay, so this class is on applying what we've learned in fluids. Yeah, so um, it's really both the classes that we did. One was on trying to understand fluids in general, and the second was really focused around buoyancy force, Archimedes principle, and so on and so forth. So um, here's the first virtual lab, and this one is called Under Pressure. You're going to need this to do some assignment questions, quiz questions. Okay, so the arrangement is pretty simple. There's a tank, okay, and you can vary the fluid in the tank. So you can make it gasoline, water, honey, or anything in between. And as you vary the slider here, that changes the density. Yeah, as you can see, changes the density. So for now, I'm going to just stick it at water. Right, just keep it to water. The second thing we can fix is gravity, and since we've generally worked with 10 meters per second squared as acceleration due to gravity, we'll keep that as the setting. Okay, now this thing here in the top, if I put a ruler, this ruler appears, which helps us measure water levels, yeah, which we want. Okay, we want to measure those water levels, and remember that the bottom is 3. Okay, somewhere around there, that's 3 meters, and this is 0, 1, 2, 3. If I check grid, then these lines appear, which tell me where is the 0, where's the 1, where's the 2, and so on and so forth. The other controls, this control here is the water inlet or the fluid inlet. This control here is the fluid outlet. All right. Everything clear up to this point? Any trouble? Okay, so let's start it off. Let's use this outlet control and let's empty the tank. Okay, so I've turned the outlet control on, and you can see that water is going out of the tank. And there, the tank is empty. Right? The tank's now empty. Now, look at the reading on this pressure gauge. This is a pressure gauge, and this tip, bottom tip, measures the actual pressure itself. All right? That's where the pressure level is. As you can see, the pressure is atmospheric pressure, and you can see this is 103.367 kilopascals. Now, if you remember, in class we had studied that 1 atmosphere is actually 101.325 pascals. So why this difference? Yeah, real atmospheric pressure is 101.325 pascals, or kilopascals, I'm sorry. But we see from this pressure gauge, and let me bring it down to 0 level, so that makes it sea level. We can see that the pressure is about 103.392. Why this difference? Anybody? Anyone got any idea? Why are we getting this higher reading? Okay, so you know that atmospheric pressure is due to the height of air above the Earth's surface, yeah, or rather the weight of air above the Earth's surface. Now, what is acceleration due to gravity correctly on the surface of the Earth? It's 9.8. What we've set here is actually 10, and therefore doesn't it stand to reason that if acceleration due to gravity is 10 meters per second square, air pressure should be higher? Remember, air pressure of any fluid is given by rho gh. So g is where rho is the density of the fluid, h is the height of the fluid column, g is the acceleration due to gravity. So if we've increased this g number from 9.8 to 10, we should get a higher level of atmospheric pressure also. Yes, do we agree with that? It's just because we've changed the value of g. Do you agree with this? Okay, so that's the reason. Yeah. Now, just very briefly, what is kPa? kPa is kilopascals. Remember that pascals is the unit of pressure in the SI system. That's newtons per meter square. Kilopascals is kPa, and that's thousands of pascals. Okay. All right. So now let's drag this inside the tank. So let's start at the zero level, and we know that at the zero level pressure is about 103.392. Okay. Now look what happens. Okay. As I start lowering the gauge into the tank, what happens? Observe what's happening to the reading. Can you see that as we go down, the pressure increases? As we're going lower and lower, pressure increases. Do we agree with that? And that occurs why? That's because the height of the air column, even though the tank is empty, there's still air in it, right? So the height of the air column is increasing because at this point, it was only from here up to the top of the atmosphere. Here, it's from this 3 meter mark here at the bottom all the way to the top of it. So there's this extra difference between the 0 meters and the 3 meters line. That's the extra height of the air column, and that's why this registers a slightly higher pressure than the pressure at 0. Is this clear? Okay, let's also try and move this along the 2 meter line. Let's move it horizontally. Okay, what's the pressure? It's about 103.417. Now we're going to move it horizontally along this line. Can you see that the pressure doesn't change as long as I keep it on the 2 meter line? Yes, the pressure doesn't change. And that's because what you're interested in is the vertical column of height, the vertical height above the Earth's surface. And as long as this level doesn't change, everything is from here, this 2 meter line. All my measurements are from there to the top of the atmosphere, and that's going to give me the same value of pressure. Okay, so now let's kind of measure what are the levels we get. So what did we get? Somebody please write this down. So we get 103.393 at the 0 meter mark. If we take it to the 1 meter mark, we get 103.405. If we take it to the 2 meter mark, we get 103.418 roughly, yeah, 418. And if I take it all the way down to the 3 meter mark, I get roughly 103.43. Yeah? Do we agree with these readings? Okay, very good. Now, let's see what happens per meter. Okay, so let's compare this level, which was 103.32393, I'm sorry, at x equal to 0, yeah, at the sea level mark. If you go to 1 meter, it's 103.405. If you subtract the difference, it works out to 103.405 minus 103.393. That's 0.012 meters. I'm sorry, kilopascals for 1 meter of depth. Now let's measure the difference between 1 and 3. Okay, so here it's 103.405. As we said here, it's 103.418. Yeah, that's the measurement over here. So the difference, 103.418 minus 103.405, is again 0.013. Yeah, the previous one was 0.012 kilopascals. This time it's 0.013 kilopascals. Let's also measure this difference. Yeah, we've got 103.43 here, and we've got 103.418 here. The difference between the two is 0.012. So do we agree that roughly we get, for every meter of height of the air column, we get about 0.015 kilopascals of extra pressure, of change in pressure. Do we agree with that? If the height changes by 1 meter, the change in air pressure is about 0.012 kilopascals, or that's equivalent to 12 pascals. Yes? So we've just done those measurements. Yeah? So that should be quite obvious. Okay? Alright. So does this value make sense? Let's try and rationalize this first. Does this even make sense? Let's try and see if it does. So if you think about it, air pressure, yeah, is what? Or rather, density of air is what? Density of air is about oops, I'm sorry, this is terrible. Just give me one moment, please. Why don't I just use the class board? Why am I going elsewhere? Okay. So here we are, here's the class board. The density of air is about 1.2 kilograms per meter cube. Okay? So therefore, if you wanted to calculate the pressure due to 1 meter of air, that would be H rho G. H is 1 meter, rho is 1.2 kg per meter cube, acceleration is 10 meters per second square. That gives you 12 pascals. Okay, that gives you 12 pascals, which is equal to 0.012 kilopascals. Isn't this what we just got? Okay, so it does make sense. This value does make sense. This experimental value you're observing does make sense. And this is a key part you should learn about doing experiments. You always need to check whether your values are sensible or not. Yeah, and if they're not, then you have to look at your experiment many times over. This is something you do with all experiments. Okay? Alright, let's go back to our experiment. Now, I'm going to drag this back to the 0 line. Alright, 0 meter line. Now I'm going to use the inlet control and add water so that water reaches up to the up to the 2 meter mark. So 1 meter of water. Yeah, the height of the water level should go up by 1 meter. That's what I'm going to do. And there we go. So I open it up. We're getting water in. There, I've let it go. Okay, so it's just a little bit extra, so I'm just going to let a little water out. Okay, there we go. Yeah, so now water is up to the 2 meter mark. It's actually just a little bit below. So I'm just going to add a little bit more. There. So now that's water. The height of water I've added is 1 meter. So it's 3 minus 2, so that's 1 meter. Now what am I going to do? I'm going to measure the pressure at this 2 meter mark level, and I'm going to measure the pressure at the 3 meter mark level. Okay, that's what I'm going to do. Let's do the same calculation that we did. So for air we said that for 1 meter of air, we are going to get a change in pressure of about 0.012 kilopascals or 12 pascals. Let's see what we would get if we were to do the same thing for water. So again we apply P equals H rho G. Again H is 1 meter of water. What is rho for water? It's 1000 kg per meter cube times what is acceleration due to gravity? 10. So we should get about 10,000 pascals, or that's equivalent to 10 kilopascals for every meter of water. Do we agree with this? That's what we should expect to see. Okay, very good. oops, I'm sorry, wrong experiment. Here we go. Alright, so now let's measure the pressure at the top, at the 2 meter mark. It's still the same, 103.41418 or something like that. Yeah, that's what we got last time, and that's where it still is. Why is that? That's because above this 2 meter level nothing has changed, right? It was still a column of air, and it's earlier, and now it's still a column of air above this 2 meter mark line. So nothing has changed, therefore the pressure reading is the same as earlier. Do we agree with this? Now let's estimate what should be the pressure reading we get when I take this pressure gauge to the bottom. It should be this pressure plus another 10 kilopascals, right? We just calculated that per meter of water there should be 10 kilopascals. So, but let's remember one more thing. So that's our measure. How does it change? Remember that what we had at the bottom here was, if I remember correctly, 103.43 when we had only air. Okay, now we want to estimate how much does this change relative to that. Okay, that's what we want to do. So let's put this down. Let's look at the absolute bottom. How low can we go? And we get about 113.4 pascals. Yes, do we agree with that? That's the reading we get. What's important to notice here is that this water that we've put here has taken away some of the air column. Yeah, earlier there was air here, so when we measured the height at the 3 meter mark, we were also measuring the weight of some air. Now that air is gone but has been replaced by water. Yes, so the change really from the previous experiment is we take the previous number, which was 103.43. Let's just do the math on a whiteboard. So the previous reading, call it P3, was equal to 103.43 kilopascals. From this we've taken away 1 meter of air, and per meter of air we lose 0.012 kilopascals, which we calculated, and to this we've added 1 meter of water, so for that we get 10 kilopascals. Okay, how much should this be? Someone do this calculation very quickly. Anyone? How can it be, Alicia? 103.43 minus 0.012 plus 10, right? That has to be 113 point something, isn't it? What should you get? Anyone? Okay, I get 113.418. Okay, this is what we should observe. Do we agree with this, that this is what we should observe? Okay, and what do we actually observe? I'm switching back to the experiment. Isn't that what we observe? 113.4. So within experimental error, are we getting pretty much what we expected? Okay, very good. Alright, so within experimental error, we've managed to get what we want. Now what I'm going to do is I'm going to add more water, and I'm going to take the water level from this 2 mark all the way up to the 1 mark. Okay, and then we'll do some of these measurements again. So here I'm adding some water. There we are. Okay, just a little bit too much. Okay, we are okay now. So now I've taken it up to the 2-meter mark. Okay, now remember that when we had put no water, at the 1-meter mark, the pressure reading was 103.405. Yeah, at the 1-meter mark. What should we get now? When there was no water, it was 103.405. What should we get at this 1-meter mark now? Anyone? Egg 105. Why, Divyangi? Why are you adding 2 meters? I'm sorry, 2 kilopascals? Okay, 103.405. Exactly, because nothing has changed, right? Above this 1-meter level, nothing has changed. So if we were to place this pressure gauge there at the 1-meter mark, earlier it was air, it's still air, so nothing should have changed. All right? Now, I want you to estimate for me what would be the pressure. Remember that when there was only air. At the 2-meter mark, the pressure was 103.418. Okay, at the 2-meter mark. I want you to estimate for me what will be the pressure now, using the same ideas as we just did. You need to add something, you need to take away something. Remember, it's 0.012 pascals, I'm sorry, 0.012 kilopascals per meter of air and 10 kilopascals per meter of water. So can you estimate for me, when I take this pressure gauge to the 2-meter mark, what should the new pressure be? When there was only air, the pressure was 103.418. Can you estimate this for me? How do you get that, Alicia? Can you just write out your calculations? So 103.418 plus what minus what? Okay, so here's what I get, yeah? Just give me one moment. I think I'm just going to open another browser. Give me 1 second, please. Yes, that's the correct answer, Divyangi. Yeah, that is the correct answer. Okay, just give me one moment, please, so that I don't have to move away from the classroom. Oh dear, sorry, this is not working. So can we just go back to the classroom page again? Let me do the calculation. Okay, both of you have got it, so that's fine. I assume you know. So you start with 103.418. You're taking away 1 meter of air, and that corresponds to pressure of 0.012 kilopascals. You're adding 1 meter of water. That corresponds to pressure of 10 kilopascals. So 103.418 plus 10 minus 0.012, and that should give you 113.406. Let's measure it. Let's see whether that's what we get. So down here. Yes, so with an experimental error we agree we are getting the value that we expect. Okay, can you similarly now estimate what would be the pressure reading at the 3 meter mark? When there was only air, then the pressure was 103.43 kilopascals. I want you to tell me what it will be in this case. Can't be, no, Alicia. You're adding 2 meters of water. Each meter is 10 kilopascals. So it has to be at least 123 point something or 122 point something at a bare minimum. So your answer obviously can't be right. Remember, this time you're taking away 2 meters of air, adding 2 meters of water. So it's 2 times 10 and it's 2 times 0.012. Okay, that's the correct answer, Alicia. Okay, so again note that earlier we had 2 meters of air that we are taking away and replacing with 2 meters of water. So it's going to be the old reading, which was 103.43 plus 2 times 10 for the 2 meters of water minus 2 times 0.012 for taking away 2 meters of air, and that should give you 123.406. Is that clear, Divyangi? Okay, very good. So now you understand what's happening to pressure, how is pressure calculated, and so on and so forth. Now here's what I'm going to do. I'm going to now use this configuration. Now right now it's just a simple tank. I'm going to make it a slightly more complicated tank. Okay, this is what we have now. Alright, so it's all the same except that these grids are now in half-meter levels. Okay. Now what I'm going to do is, again, I'm going to fill water exactly to the 1 meter mark. Alright, which is what we had just now. Okay, in the ordinary tank we had water up to the 1 meter mark, and I'm going to continue to fill it up to there. Okay, there we go. Just a little bit extra. Okay, so here we are. Now what I'm going to do is I'm going to measure pressure levels. Oh, did we verify the previous one? I'm sorry, we didn't verify this one, right? We said it should be 123.406, but we didn't verify it. Let's do that. Here we go. Let's put it all the way down. So it's 123.2. So again, approximately, give or take, this could go up a little bit more, I think, 123.3. Yeah. So really these errors are simply due to essentially perhaps this column is a little bit different. Yeah, just a little bit more than 1 or a little bit less than 1, depends on that. So very minor error, but we are able to predict using our formulae. We're able to predict what we should get quite accurately. As I said, in this case, what we've done is we've changed the height of, we've changed the shape of the tank. Okay, but the vertical height remains the same. And as you can see, let's measure the pressure at the 1 meter mark. At the 2 meter mark. If you remember, you had calculated it to be 113.4, and we'd verified it was 113.4. It still is. Let's go back and check. Yeah, so at the 2 meter mark, it's 113. Oops, slightly below. There we go. That's the exact level. Sorry. It's a little sensitive to level, so you have to get it right there. Yes, do we agree? It's 113.4 here. When I change the shape of the tank, it's still 113.4. Okay? So what does this tell us? Let's also measure 3 at this level. Okay, at the bottom level. It's 123.4 here, and in this configuration also it's 123.4. Let me measure it somewhere here. Okay, give or take small differences in pressure level. Okay, so really what does this tell us? That the shape of the tank is immaterial. Yeah, shape of the tank is immaterial. What matters is the vertical height of the fluid column. That's what is of importance. Do we agree with that? Okay, finally, I want to look at this and I want to measure the pressure over here. Okay, just above the outlet valve. And can you see that it's also 123.4, but the height of the water column above it is not 123.4, is not 1 meter, right? This is the height of the water column is only this much. Yeah, here it's this much, but the pressure here, which is 123.4, is the same as the pressure here, which is 123.4. Can you see this? Yeah? So why is the pressure the same? Really, the answer is in a connected body of water like this one, yeah, they're connected. At any fluid level, at any specific level, the pressure must be the same. So the pressure here at this point is coming from this side as well as this side. Okay, so pressure acts in all directions. That's the important idea, equally in all directions if you choose any point. Is that point clear? Okay, so that's this experiment, really experimenting with fluid pressure. The next experiment is talking about buoyancy forces. Okay, that's what we're going to do. What are the controls here? I call this the block control. Okay, this is the material properties control. Yeah, and you can drag this block in and out of the tank. Here's the tank of water. You can see that it's filled with 100 liters of water. Okay, so these very simple. Those are the controls we have. So now what are we going to do? Let's select this as custom. That's what I've done, custom block. Under properties control, I'm going to make this my block. Okay. Look at the volume of the block. It's set to 5 liters. 5 liters is 5 into 10 to the power minus 3 meter cube. Now, once the volume is fixed, what we are going to do is we are going to vary the mass of this block. Okay, we're going to change the mass. The volume remains the same, but the mass changes. Okay. Now, I want you to look at this density number. Remember, density is mass by volume. So if volume is constant and I change the mass, then the density must change. Do we agree with that? Okay, so here we go. I'm increasing the mass slowly. Alright, and you can see that the density also changes. Alright, you should be able to see that. Okay, volume changes, mass changes, density changes. Now, I'm going to set the mass at its minimum setting. I'm going to take this block and I'm going to drop it into the water. Okay, how do I verify, for example, that the volume of the block is 5 liters? Look at this pressure tank reading. It's 100 liters. I'm going to drag this block into the water and I'm going to make sure it's submerged, which means I'm going to drag and I'm going to hold it there. And I'm going to note the volume reading. Can you see that the volume reading on the tank is 105 liters? And therefore, do we agree that the volume of the block must be 5 liters? 105 minus 5? Okay, but I have to hold it there. If it floats and only a part of it is underwater, then the water tank level no longer shows 105 liters. It shows accounts only for the part that's underwater, and that's only 1 liter. Okay, that's the part of the block, volume of the block that's under the water. Okay, so now I've put this block into the water. I've verified that its volume is 5 liters. Now I'm going to start slowly increasing the mass. Okay, can you tell me the density of water in kg per liter? It's 1000 kg per meter cube. So what's it in kg per liter? Come on people, not so difficult. Okay, go to the whiteboard please. Important that you should know how to do these conversions. It's 1000 kg per meter cube. Okay, so it's 1000 kg for 1 meter cube. 1 liter is 1 into 10 raised to minus 3. Yeah, liters per meter cube. So for this much of meter cube, I'm sorry, other way around, meter cube per liter. Yeah, so for 1 into 10 raised to minus 3 meter cube, how much? Simple ratio proportion, multiply these two, you will get 1 kg per liter. Is this agreed? That this is the density of water in kg per liter? Yes or no? Okay, very good. So now here's what I want you to do. I'm going to start increasing the mass. And I want you to see the density, the density at which this block just sinks. Okay? There we go, I'm increasing the mass, density is increasing. You can see that the block is sinking even more. And I raise the mass to a little bit above 5. The density goes a little bit above 1, and you can see that the block sinks. Do we agree with this? If I raise the density to anything above 1, the block sinks. Okay, and if the mass is such that it's just below 1, then you can see that the block floats. Okay, so that's the idea of density. That's how we use density. We studied relative density and specific gravity in the previous class. We said very specifically, if the density of the substance is less than the density of the fluid it's immersed in, it will float, and that's exactly what we are seeing. Okay, so now what will happen? Let's try and see why this requirement holds. What is so special about this requirement? Okay, and we'll use the buoyancy force to calculate this. So let's take the block out again. Let's calculate the maximum force of buoyancy that can exist on this block. Please go back to the class whiteboard. Okay, so maximum buoyancy force is equal to rho, the density of the fluid, multiplied by g, acceleration due to gravity, multiplied by v. This is the volume of the solid object that is immersed, that is underwater. Okay, so because this is the volume of the fluid displaced. Remember that if you don't submerge it completely, it won't be equal to the volume. It's only that part of the solid which is underwater. So now, therefore, if this V is maximum, which means that the solid is completely submerged under water, then the volume displaces the volume of the solid. Do we agree with that? Okay, so therefore now the maximum buoyancy force is the density of liquid, which is 1 kg per liter square, 1 kilogram per liter, multiplied by 10, multiplied by the volume, which we said was 5 liters. And therefore we'll end up getting 50 newtons as the maximum force of buoyancy. Okay, do you agree with this? Let's draw the free body diagram of the block. You've got buoyancy force acting up, you've got its weight acting down. Okay, so really, if this is maximum, then obviously the weight will be maximum, yeah, for equilibrium. Okay, so now therefore we equate W equals FB max, which means mg equals FB max. Weight is mass times gravity. This is mass of the block. So mass of the block must be equal to FB max, which we calculated to be 50, divided by 10, which is 5 kilograms. What will be the density of the object? If its mass is 5 kilograms, we saw that density of the block must be equal to 1. This is the best possible case, maximum possible weight of block which will float. And that's exactly what we saw. If the density was 1, it would float. Anything more than 1, it would sink. Yes, do we agree with this? That what we saw agrees with our calculations? And indeed, this is what is Archimedes' principle, right? This density, or rather, this density relationship is derived from Archimedes' principle. Okay, what will happen if the maximum force of buoyancy, okay, is less than the weight of the block, which means that the block has a mass of more than 5 kilograms. All right? Let's see what happens. Okay, I'm sorry, the other way around. What I wanted to say was, what will happen if the weight is less than the maximum force of buoyancy? All right, that's what we wanted to see. So let's set the mass to say 1 kilogram. Okay, there we go, mass at its lowest. Here's the block. Okay, I'm going to now, so we already submerged it fully, so we saw that the volume is 5 liters. We also calculated the maximum buoyancy force to be 50 newtons, right? Now if the mass is 1, okay, then what's happening? Let's please go back to the whiteboard. Then if I submerge this mass fully underwater, then FB, which is maximum force of buoyancy, is 50 newtons. The weight of this is only 1 into 10, 1 kilogram times 10 meters per second square. That's only 10 newtons. What should happen to the block? What should happen to the block? If I hold it underwater and these are the forces acting on it, what should happen to the block? No idea? Okay, it should jump out of the water, right? Because the upward force is more than the downward force. Let's see if that's what happens. So I take this block, I drag it down so it's fully submerged underwater. I know that at this point in time maximum buoyancy force is acting, which is 50 newtons. the weight is only 10 newtons, and therefore there is 40 newtons of upward force, and according to me this block should rise. Okay, let's see if it does. I release the mouse, and there you can see that it rises. Did you see that? Now you should be able to see that only a part of this block is submerged, not the whole block, only a part. Alright? Notice the tank volume setting, it's 1 liter. So it's clear that the volume of the block underneath the water surface is only 1 liter. Okay? This means that the volume displaced by the block, volume of fluid displaced by the block, is only 1 liter. Therefore, what should the force of buoyancy be? Fb in this case is equal to rho, which is 1, times g, which is 10, times v, which is 1 liter. And that gives me a force of 10 newtons. That's the buoyancy force. So now if I draw the free body diagram, the buoyancy force acting is not the maximum buoyancy force, but it's only 10 newtons because only part of the object is in the water. The weight is also 10 newtons, and now this should be stable. Do we agree with this? And isn't that what we see here? It's stable, it's floating at this level. Okay? So now let me ask you a question. If I change this mass to 2, okay, what would happen to the block? What would happen to the block if I change the mass to 2 kilograms? Okay, Alicia says it will sink a little. Do you mean all the way, or will it still remain partially submerged? Will it submerge fully? What will happen, Alicia? Divyangi, what will happen? Partially submerged. Okay, let's try it out. So I'm going to change this mass to 2. Oops, I changed it too much. So I'm going to change it to 2. What was it earlier? 1, right? Let me start with that case. This is the 1 kilo case. I'm going to change it to 2. And as we can see, it sinks a little bit more, so that the volume of water displaced now has changed from 1 liter to 2 liters. Therefore, the force of buoyancy now at this level, when it's 2 meters, Fb equals rho GV. Rho is 1 kg per liter, G is 10, V is 2 liters. Oops. That gives me a force of 20 newtons. So I've got 20 newtons acting upwards, that's the force of buoyancy. And I've got the weight of the object acting downwards. Mass is 2, acceleration due to gravity is 10, 20 newton downwards. This should be stable. And indeed, that is exactly what we see. It is stable. Okay? And we can see that as the mass has increased, it's had to displace a greater amount of water. According to Archimedes' principle, buoyancy force equals the weight of water displaced. The weight of water displaced now is 2 liters, therefore the weight of that is 20 newtons, and that balances out the 20 newtons weight of the object itself. Okay? Alright, now what can we do? What will happen if I enter 4 kilograms here? What's likely to happen? what will be the volume of water displaced? It will sink further into the water clearly, but will it sink all the way? Will it sink partially? Okay, let's try and see, yeah? Clearly, it's going to sink a little bit more. Oops, why does this keep happening? Okay, 2 is what we had. I'm going to change this to 4. Okay, as we can see, it's still floating, but only a little part of it is out of the water. Alicia, either the whole body floats or the whole body sinks. What you mean is only a little part of it will be not submerged, yeah, will be projecting. That's what you mean. You can't have only part of the body floating and part of it sinking, right? Sinking means it goes all the way down. Okay, is this clear? How buoyancy force works, how weight works, and so on and so forth. Okay, very good. So now what I'm going to do is I am going to just give me one moment. I'm going to do one problem for you all. Just give me 1 second. Sorry, it seems to be taking a little bit of time, but let's just be a little patient. Okay, there we are. Alright, so here's what. Okay, there we go. Now, what I want to do is okay. So here's the question. There's a wooden block of dimensions length 30 centimeters, width 30 centimeters, and height 15 centimeters. It's placed in a bath of water. The density of water is 1 kilogram per liter. Assume that a face measuring 30 by 30 centimeters is the lowermost face of the block when immersed in the bath. The block floats with 5 centimeters projecting outwards. You need to calculate the density of the wood. Okay, so just exactly the experiment we've seen, but we're going to do a little bit more. Without doing the experiment, we're going to try and just do the numbers and see how it relates to what we've done. So here's the situation. Yeah, first it's best to draw 30 centimeters length, 30 centimeters width. This is the bottommost surface of the block. So this must be 15 centimeters. And it's projecting so that only 5 centimeters is out, 10 centimeters is under the water. Okay? So now, how can we go about this? We need to calculate the density of this block. What that really means is we need to figure out what its mass is, because we know its volume, right? We are given the dimensions, so we know the volume of the block. Okay? Now, we can figure out how much of the volume is under the water. Okay? The portion of it that's underwater, That's the amount, that's the volume of fluid displaced, and therefore that must be the buoyancy force. If that is the buoyancy force, we can equate that to rho GV. Yeah, I'm sorry, other way around. We know V, that's the volume of the solid under the water. That's the water displaced. This is the weight of the water displaced, which is according to Archimedes' principle. That's the buoyancy force. Then we can equate the buoyancy force to the weight of the block, and therefore W is equal to mg. So we can say mass of the block is equal to this buoyancy force by force of gravity. We can then calculate the density as mass of the block divided by the total volume of the block, not this V. This V was only the amount that was under the water. This V is the total volume, and this ratio will give us the density. Is this clear? Is the approach clear? Okay, so can you please go ahead and solve the question? Here's the situation to help you out. And here's the method that we spoke about. Can you please work this calculation through? Okay, let's take it step by step. Yeah, what is this volume V that is under the water? 30 centimeters length, 30 centimeters breadth, 10 centimeters height. What is the volume in centimeter cube? Come on, people. What is the volume of a cuboidal structure? Length into breadth into height. Length is 30 centimeters, breadth is 30 centimeters, height is 10 centimeters. What should be the volume underwater? Divyangi, come on. 9,000 centimeter cube. How many liters is this? Is equal to how many liters? $99 liters. 9 liters. Okay, so this is the volume submerged. So therefore, what is the buoyancy force? Can you calculate the buoyancy force now? FB must be equal to rho GV. Rho is 1 kg per liter, G is 10, V we calculated is 9 liters, this is in kg per liter, so the liter cancels out, this is fine. What do we get in newtons? as the force of buoyancy that is acting when it's floating? Newtons. So therefore now 90 newtons must be equal to the mass of the block times gravity. Yeah, and this thing is just the weight of the block. Okay, because it's holding in its position, it means that the force of buoyancy from the free body diagram, weight of the block must be equal to the force of buoyancy acting on it. We've calculated this as 90 newtons. That must be equal to mass of the block times gravity. Therefore, mass of the block is how much? Mass of the block is 90 by G, which is 10 newtons, which is equal to how much? Alicia, you can't just write numbers, you have to put units when you're talking about physical quantities. 9 kilograms. So what is the density of, what is the total volume of the block? Total volume is 30 length, 30 breadth times 15 height. What is the total volume of the block? In liters, please. Alicia, 13,500 liters. Think again, that's a lot of volume. Think about your units. 13.5 liters precisely. So if it is 13.5 liters is the volume of the block, mass of the block is 9 kilograms, what must be its density? Density equals mass by volume. Please calculate the density in kg per liter. Come on people, 9 divided by 13.5 is how much? I have no idea why all are taking so long. I need more precision, Alicia. 1 decimal is not enough. So density equals mass of the block by volume of the block. We said mass is 9 kilograms, volume is 13.5 liters, so we get approximately 0.67 kg per liter. Do we agree with this? Divyangi, agreed or no? Okay, so that's the answer that we need to get. That's the answer we found. Now I'm going to leave you with one thought. Okay, what is 0.67 as a fraction? 2 by 3. Do we agree with this? Okay, you have to agree with it, yeah, because it's a fact. So now let's look at what's happening to the block itself. What fraction, remember what's out of the, this is certain amount of volume. Let's call this, what I want you to calculate is what is the fraction of the block that's submerged in terms of volume. What fraction of the volume of the block is underwater? So that's really, this is 30 into 30 into 10 divided by 30 into 30 into 15. Cancels 2 by 3. Can you see this? I want you to think about how this makes sense. Why is it that you get this number? That this number, the proportion of volume underneath the water surface, is equal to the density of the whole object. I want you to think about this. Okay? It's pretty cool, isn't it? Alright, so I want you to think about that. In the meantime, could you please fill in the feedback? Just one moment, let me give you the the link for that. Okay, here's the link. Please provide your feedback, and if there's any questions, please ask, otherwise you're free to leave.